Okay, hello everyone. This is Linguistics 488. Uh, uh, this half-hour video is is a recap of what we have done in the first 7 weeks in preparation for the upcoming exam um, and for future reference. So basically, we're talking about um, natural language modeling. So the overall picture is in scientific modeling, we have, let me share my whiteboard with you. Um, uh, um, so we're talking about um, theory of grammar leading to possible models of the the grammars in that theory. So we have essentially a theory of grammar, and we want this to lead to what you can call possible grammars. So let me just write this better. And from these possible grammars, essentially, um, we want to move to models of grammar. And we do that using natural language data. That's the idea. And from this, we want to come to model development and selection. In other words, after all, there will be multiple models, and we want to develop models with certain data parameters and training parameters to come to a point where we can assess the models and select one among them. And this is usually done, again, by data. This is supervision, sometimes self-supervision, or sometimes supervision, and parameters. Okay. And from this, what we want to get is to sort of by model selection, we want to come to a preferred model of grammar. That's the idea. So uh, the point of having a solid and modelable theory of grammar is to give you a vocabulary here to write possible grammars and a nomenclature. In other words, tools and techniques um, and terminology and concepts to help you see that these grammars are possible grammars and then they are, in a sense, modelable. Usually this comes with categories. You have to have a clear notion of what's a category in that grammar. and you've seen two kinds of categories so far. One is functional, that I'm going to talk about. Essentially, all categories of categorical grammar are functional categories. And the distinction between this and relational categories are important, so I'm going to talk about that. And of course, rules, which follow as a consequence of having a theory of grammar. And we have seen two kinds. One is application, function application, that is. The other was composition. I'm not going to define them because we've done that in class, but roughly speaking, function application is like if you have a function looking for for y to the right, and you have y on the right, this is going to give you f by applying f to a. So this is the syntax part. So these are syntax parts of the category, and this is the semantics. So you can see that essentially semantics is driven by having the semantics follow syntax. So if syntax applies, then semantics apply. If syntax composes, then semantics compose. So let me show you composition of semantics. So if you let me show you composition. Okay. All right. So essentially, again, this is syntax. And this is semantics. So as you can see, when syntax applies, semantics just follows. The reason why we say syntax semantics applies only when syntax is succeeds is because if syntax does not succeed, semantics essentially does not have to apply or compose, because essentially it's equivalent to saying that this is not a grammatical structure in combining these two categories. So just to give an example of that. If let's say you have a function called f, this is an example, and it's looking for y, and you have z, which is a, and let's just say y is not the same as z. Then combining it to mean fa is ungrammatical. Okay. And the reason for that is that although syntax semantics if you look at semantics, it's just function application. So essentially, x over y is a function, and z is an argument to that, but it's not an argument to that function. Therefore, this combination does not apply. Okay, so these are critical concepts for us to know um, uh, what is possible and what is not, and that's given by the nomenclature and rules and possible consequence of theory of grammar that's going to be affected in a model. In other words, when you have possible grammars here, essentially we're saying that everything in a possible grammar is essentially well-formed combinations of things and well-formed elements in whatever language you're studying. So these are essentially combinable. Okay, but they are combinable with certain categories and not other categories. So they have selective responses to the kind of categories you have in grammar. So that's the whole idea. And so in this course, what we're trying to do is to do, let me move on to another slide. We want to do scientific modeling. Okay, and you want to know the difference from engineering modeling. Okay. Now, engineering models are essentially about performance, robustness, this is all about performance, robustness, and reliability of a system before deployment. In other words, you're going to deploy a system. It's just that you want to make sure that it's is high performing, robust, and reliable, so that people can take results comfortably. In a scientific model, what you do is essentially you prepare in a scientific modeling process, you're preparing a theory for experiments. In other words, you want to make sure your theory of grammar, in our particular case, gives you all and only the kind of models that are inferable from theory. And you take these models, and since there are multiple models and there are many natural languages that are essentially naturally acquirable, then you let the data here select the model so that your grammar is a faithful reflection of whatever language you're studying, not any language. And for that, you need to have models of grammar so that you can choose among them. And that's the whole idea in the middle box. And that you can only do by saying what kind of data you're exposed to and what kind of training I can done on that data. It can be done on the data so that it's a faithful reflection of the possible models of grammar. And there are different kinds of parameters in this endeavor, so I'm going to talk about this, but for the time being, I think this much is good enough for our purposes. So we're talking about essentially the differences between scientific modeling and engineering modeling, and this is scientific modeling is what we're trying to do. Okay. One thing in both cases, we know that modeling requires some kind of parameters. Essentially, a parameter in science is a set of values that identify a data point. In case of us, a data point is essentially a grammar. Among the many possible grammars that you can have for natural languages, every data point is essentially a grammar, which is itself a collection of entries in the grammar, elements of grammar, so to speak. Okay. So in terms of parameters, we have data parameters. Which essentially say this data in this grammar is participating in that much belief in it, some kind of weight, or in some cases probability or whatever. And then we have hyperparameters. These are most like training parameters. Hyperparameters, as the name implies, are these are over data. That's why they're called hyperparameters. Okay. Examples like learning rate. When you're training, you're going to have a learning mechanism, and there's going to be a learning rate. How fast are you expecting the system to learn? And of course, another one is, well, okay, how fast you learn, but how often do you change your belief in the network as you learn? This is called learning rate in some kind of meaning. In what frequency and you change the learning rate is essential. So these are essentially modeling tools for model development that I mentioned before. And after that, in like LLMs and engineering models, there are response parameters. Sometimes like some called heat. How much of creativity you expect out of response? Is it very formal? Is it very creative? In other words, the output. That's why they're called response parameters. These are the kind of stuff that you set after training. And there is, of course, what's called fine-tuning. Fine-tuning essentially refers to adjusting your training in such a way that when it comes to sensitive material like racism and others, or criminal activities, you want to fine-tune your system and not to get into traps and difficult questions about these. This is essentially done after fine-tuning in some cases, and sometimes rule-based, in other words, manual filtering, so that you can rule out certain names of associated with hatred and others, and so that when your system as an engineering model is confronted with these names and questioned about these things, it just says, I don't know anything about this. So if you've noticed in large language models, there's a very typical response when you ask this question, are you conscious? And they respond almost univocally that they're not conscious at all. And that's essentially a rule-based response from these models, because they don't want to get into the trouble of dealing with the further consequences of answering, yes, I'm conscious. So this is So this is the kind of stuff between this large language models and scientific models. So the difference is scientific models are transparent. Okay. Um, the reason for that is that um, um, uh, um, their results and training must be independently replicable. In other words, other people, other scientists can take this result and get a response, and they should be able to compare that with what is being reported about this scientific model. And if there are response parameters or other intervening material, they cannot do that. So that you won't see response parameters, fine-tuning, or rule-based systems in scientific models. That's one crucial distinction that we're going to continue to talk about in class. Okay, so this is essentially how a scientific modeling of grammar connects to a theory of grammar, how a theory of grammar gives you possible grammars so that you can conceive the idea of a model of a grammar. And then you take that model of grammar and select among the models to see how the language you're studying um, is adequately or inadequately represented by a model. So that's the idea. So what could these be in terms of natural language? So if you're, for instance, studying word order in a language, and if your grammar is exposed to something like English, you would expect it to converge into subject verb object, because that's what the basic word order is in English. But if it's exposed to Turkish, it would be subject object verb, because that's the most common word order in Turkish. But you don't want to say that a priori. You want this to be figured out from data itself, which means the theory of grammar must allow any kind of word order to be basic in the first place, so that by modeling, you can choose one of them. Okay. So that's the idea. And we have essentially uh, uh, seen um, uh, functional and relational categories. Functional categories So um, uh, essentially, the idea is going to this is going to come down to this: the idea of dominance in natural languages and linguistics. Dominance is a relational concept. Um, uh, but uh, the structure of a clause is actually functional. Why? Because it can be uniquely determined by the matrix verb. So just to give you an example for one and two, one, you can think of like uh, noun phrase, verb phrase, like I, and verb phrase, noun phrase, like chocolate. Okay. The reason why it's functional is if you read top down, um, S has two elements, MP and MP. Um, Therefore, it's not a function going from top to bottom. Okay? The second one basically says, well, if you look at this structure um, functionally, if you look at this structure bottom up, everything has a single parent, so it's essentially functional. And if you look at the structure of the clause, it's essentially determined by the main verb. So if you have like I like and chocolate, and if this is a verb, this is a verb which is transitive. Um, um, and this category, as you know from class, uh, that it's going to get the sub object first to give you this, and it's going to give you a subject next to give you this. So in the end, you get the same result, but the way you obtain it is very functional here and relational here. Okay, so that's essentially the major difference. And if you do this experiment um, with embedded clauses, you see the power of having the verb determine the entire clausal structure. So let's just say again, like MP, VP, I, V, S, like I think, uh, and then say you like chocolate. The all again, it's relational, looking this way. Why? Because if you look at S, you have MP and you have VP. So there are two constituents of S, not one, as in functions. And then you look at VP, there's V and S. There are again two constituents. So this is not like a, a function, but relation looking this way. But if you look the other way, it's going to be quite functional. So what do? The crucial point here is that no matter how you look at it, we know from empirical data that domain sub predication here is about thinking, not liking. So I am doing the thinking, and my thinking is that about your liking. Okay, so you want think to determine the overall nature of the clause. So if you write categories for them, this will be noun phrase, which as you covered in class, this will be like, okay, I'll take a subject if you give me an S to the right. This is a noun phrase. This is a transitive clause, a transitive verb. So you get from this, you get S under MP by application. And by combining that and that, you get S. By combining this and that, you get S under MP. And then combining that, you get S. Okay. And if you look at, if you write some semantics for this, like that, if you write semantics for this, it will take two arguments, one for this, one for that. Let's say lambda p, lambda x. This will be like think px, which we know is actually a structured representation. This is like think px. So this is actually a structured representation. Okay. Here, what you get is essentially lambda x think like chocolate u x, and from this you get, by taking I for x, you get think like u chocolate I. So the overall meaning of the clause is determined by the matrix verb, not the embedded verb. That's the whole idea. And the point of this for modeling is, if all your categories are like this, then the verb is going to give you the element of verbs in your grammar is going to give you all the modeling power to try out different kinds of training on the kind of structures that you see in the language. That's the idea of the course that we're going to talk about. And this is what we've covered so far in class. So I'll stop recording now and probably add a bit more if